All right, section 1.1 is a very brief preview of calculus. In particular, what we're going to look at in this section is kind of comparing calculus to precalculus and the differences between the two, the types of problems that you see presented in the two. And we're going to look at some sort of approximations for how we can think about solving those problems using precalculus techniques, things you've seen before, with a calculus-related topic. So to start with, what is calculus? Calculus is the mathematics of change. Okay, I am not in any way, shape, or form expecting you to draw these pictures on here, okay? But these are straight from your textbook, so these are on page 47 to 48. Okay, so just put that note in there. I think, did I say have the wrong pages on there still? I probably did. Okay, I did get it fixed. Good. So these are some different ways to think about differences, I guess you could just say, between precalculus concepts and calculus concepts. So on the left-hand side, we have without calculus, and then on the right-hand side, we have with calculus. So if we don't have calculus, we can find y values when we have x values. If we've got a function or a graph of a function, we can look at the ordered pair and where things are located and say, oh, at the x value of c, I can figure out what the y value is. So we can do that without calculus. But with calculus, we can also find the limit, which means what it's getting close to. And in particular, you know, a lot of times the picture on the left, it's actually getting close to the dot that is, you know, filled in. But if you see the picture on the right, there's an open circle, and if you just try to plug in the value for x, it doesn't give you a value for y. It gives you errors from your calculator's perspective. So with calculus, we're able to do that. Without calculus, we can calculate slopes of lines. Do you guys remember how to do slope? Tell me something you remember about slope. Okay, that's an equation that has slope in it, y equals mx plus b. What else do you remember about slope? I see movement of lips, but I don't hear voices. What do we got? Somebody tell me something you remember about slope. Okay, that's with calculus. We're going to start without calculus before you have calculus. You're right. Change in y over change in x. So you see it written like this sometimes. You might see y2 minus y1 over x2 minus x1. You might have thought about it as rise over run, right? Nod your head if you know what I'm talking about now. Okay, everybody's good. Fabulous. When you're dealing with calculus, you do deal with derivatives. What you're looking at is you're looking at slopes not of straight lines, but of curves. So you're looking for how sharp the curves are. What's the slope on a curve? And as you can see, I mean, I don't have 2 points that I can measure this with, right? So it doesn't work quite the same way, but there's other options. When you're dealing with calculus, you can find slopes of secant lines to curves. So secant lines are lines that cut through a curve twice. Okay, so they take this point and they cut through the curve with a straight line. If you're dealing with calculus, you can find tangents to curves. So tangents are, if you remember like from geometry, they just touch a curve, right? You've probably dealt with them with circles. You just touch the circle and it bounces back off. Without calculus, you can calculate the average rate of change. Right, how long it took me to get somewhere, how far I was driving, and so I can get an average speed that I went. With calculus, you can find instantaneous rates of change. That is, how fast is something happening right now, not over a span of time. You can find the curvature of a curve without calculus. I'm sorry, a curvature of a circle is what I just read it wrong. The curvature of a circle without calculus. With calculus, you can actually find the curvature of a curve. Without calculus, we can find the height of the curve at a specific point, much like the very first picture that I did. But with calculus, you can actually find the maximum height of a curve on an interval. In 3 dimensions, which we won't get to in Calc 1, but it's true, you can find the tangent plane to a sphere without calculus. With calculus, you can find the tangent plane to any surface. Hopefully you're getting the picture that with calculus you just have more flexibility. It allows you to do things in a more general sense instead of being very specific. Circles, spheres, very specific without calculus. You can find the direction of motion along a line without calculus. You can do that along a curve with calculus. You can find the area of a rectangle without calculus. But you can actually find the area underneath a random curve with calculus. You can find the work done by a constant force without calculus. You can find the work done by a variable force, something that's changing, with calculus. You can find the center of a rectangle without calculus. You can find the center of any arbitrary region with calculus. You can find the length of a line segment without calculus. You can actually find the length of a curve or an arc with calculus. So lots and lots more flexibility when we have calculus techniques. So, oh, sorry, I thought that was the last of it. These are three-dimensional shapes. We'll move through them quickly. So surface area of a cylinder on the left. With calculus, you can actually find a solid of revolution, so it's a variable type shape. The mass of a solid of constant density on the left, a solid of variable density on the right, the volume of a rectangular solid on the left, the volume of this region under the surface on the right, a random region. And without calculus, this actually, the last part here is Calc 3, which I taught last semester. You can find the sum of a finite number of terms without calculus, but in order to do an infinite number of terms, you need calculus techniques to do that one. Let's see. There we go. All right. So what we're going to do is we're going to do a couple of examples using calculus so that you can see how we can think about this. So here is the tangent line problem. So a secant line is a line between 2 points on a shape. I mentioned that before. And a tangent line is a line touching only one point on the shape. So we can do that for circles. That's where you usually see it done first in your mathematical background. So a circle, there's a secant line. And for a random curve, that would be a secant line. It cuts through the graph. If you were doing a tangent line, so this secant line are the ones I underlined in black. I'll do the other one in red. So tangent lines. So a tangent line to a curve means that, to a circle, it means it just bounces off, right? It touches it once. And for a random curve over here, same thing. It's going to bounce off of the curve. Those are tangent lines. So again, remember, secant lines are precalculus. Tangent lines need to use calculus. So let me show you what happens when we think about the two different things. I didn't mean that one. With calculus versus precalculus. So in precalc, we can find the slope of a secant line. We do this by using, so we use 2 points on the curve and calculate the slope between them. So for example, we had this curve, and we took this point, and we took this point, just two random points. We could connect them with a line segment or a line. Do a better job than that. All right, and we could calculate the slope of this line. One of these points would be x1, y1. The other point we could call x2, y2. And we would literally calculate, like we mentioned before, y2 minus y1 over x2 minus x1. And we'd find the slope. And you start finding slopes probably as early as 6th or 7th grade, depending on where you hit pre-algebra in your career, maybe 8th. Okay, but pre-algebra. All right, so in calculus, what can we do? Well, in calculus, we can find the slope of a tangent line. We do this by using secant lines. Where the points get closer to one another. So if you think about, I'll try to roughly draw the same curve. Okay, I think that's pretty good. And if I were wanting to find this point right here, I'll mark it in red this time, the slope of the secant, or the slope of the tangent line would be something like that. Agreed? Bouncing off the curve. So that point that I originally drew over here is pretty far away from that red dot. And when I put the two lines together, like I connect it with a line, put the 2 points together with a line, and create that secant line, it looks nothing like the tangent line, right? I mean, it's nowhere near what the tangent line is that I'm trying to get to. So if you think about it, this would have been the secant line. But if I let the point get closer to the point that I want, and I calculate the secant line, and I let the point get closer to the one I want, and I calculate the secant line, can you see how those lines eventually become, if the points get close enough together, the tangent line? Right? I wish I had like an animation to show it. As the points get closer together, as the left-hand point in this, or sorry, the right-hand point in this case moves closer to my left-hand point, I get points close enough together that I can get a pretty good approximation of that tangent line. That is called a limiting process. We're limiting the difference. We're making the difference between the 2 points very, very, very small in order to get really close to the actual point we want. So that's actually the idea of what calculus allows us to do, is it allows us to calculate that second quantity. And I want to show you another example of that, and that's an area problem example. So this first example is related to the concept of derivative, for those of you who have heard of that before. And if you haven't, again, don't worry about it. But that's what this is related to. The second example is related to the concept of antiderivative. So in the area problem, we know we can calculate the area of certain shapes. So in pre-calc, we can find the area of certain shapes. And a few of those would be, this is not like a complete list, but things like rectangles, triangles, circles, and I'm going to say etc. because the list, of course, is much longer than that, but those are some of them. And we use formulas. Most of which, not all, but most of which are based on the area of a rectangle. And that formula, of course, is area equals length times width. So we find an area of a triangle using that formula, a variation of it. You find the area of a trapezoid using a variation of that, parallelograms using a variation of that. A lot of them are based on areas of rectangles. But in calculus, we can use the area of a rectangle to approximate the area under a curve. Then let the width of the rectangles approach zero. So let me draw a picture of what I'm referencing in case you haven't seen what that means before. So this is just a random curve, right? And if I start here and I end here, this particular shape is actually pretty close to a rectangle already, right? I mean, it wouldn't be horrible. If I used a shape that was more variable, like the one that I started with over there a moment ago, it's a little less like a rectangle, okay? But you've probably had the experience with your calculator before that when you've zoomed in too far or you've zoomed out too far, the picture doesn't have quite the right image that you'd expect. If you zoom in close enough on a parabola, for example, it looks like a line. Depends on the portion you're looking at, but it could very easily. So when you zoom in and zoom out, it has sort of the appearance of it being straight when maybe something's not. So the idea here is that if I made more and more rectangles, and if I took more and more rectangles where their widths get closer and closer to zero, that the little bitty pieces look more and more all the time like actual rectangles. Because the curve itself looks more and more straight the more you zoom in. Does that make sense? So if I had more and more and more rectangles that are really, really, really tiny, and I added all their areas together, I'd get really, really close to the area of the actual shape I was looking at. And that is a process of calculus, allowing us to have infinitely many rectangles with very, very infinitesimal like width, so that I actually get the area of the shape itself that I was looking for. Okay, so both of these calculus techniques, this one with area and this one with the secant lines becoming the tangent line, are things that we're going to have to develop over time. You're not going to leave today knowing exactly how to do them, okay? But we're going to look at some examples of how we can approximate that kind of an idea. So we're going to take the first example. It says to decide, in fact, these are the directions for both problems we're looking at. Decide if the following problem can be solved with precalculus or whether calculus is required. If you can do it with precalculus, do it. If calculus is necessary, then explain why. And use a graphical or a numerical approach to estimate a solution. Okay, so the first question says, consider the equation f of x equals 4x plus 3. What is the slope of this curve at x equal to 2? So, the first thing you need to do is to look at the equation given and try to figure out what is this an equation of? It is a straight line. Okay, everybody good? Straight line. So, although the phrase says of this curve, it's using a very general phrase to encompass a lot of things. The shape that we actually have is not curved the way we think of curved, right? It's a straight line. So in this particular example, you could replace that phrase with, what is the slope of this line at x equal to 2? What is the slope of this line at x equal to 2? It's not 2. It's 4. So where did the 4 come from? Yeah, the m. So you had mentioned, Frankie, earlier that you remembered this equation, y equal mx plus b. And I suspect most of you do remember that equation. You should. It's a really popular equation of a line. And the m in this represents the slope. So if we have an equation that is a line and it is in this form, the slope is really easy to identify. It's simply the number in front of x. So this is actually a precalculus concept. And in particular, the reason it's precalculus is why. What is that makes this precalculus? Because it's a line. If this were a legit curve, like a parabola, it's precalculus. I mean, it's calculus. It's not precalculus. But this is a line. So this is precalculus because we're dealing with lines. And you know from precalculus ideas that the slope of this then is 4. And that's the answer to the question. So on these problems, when you encounter the ones that are precalculus, they're going to be answerable pretty quickly. They're pretty straightforward. You just need to make sure you're deciphering that they really are precalculus, of course. Okay? So if I gave you 2 examples and one of them was precalculus, what do you expect my other example probably is? It's probably calculus. You can't do that when you get to your homework because there's a smattering of a bunch of different things, right? But for the examples in class, this is what's going on. So this says, consider the equation f of x equals 3x squared plus 2x minus 4. What is the slope of this curve at x equal to 2? Okay, the question is almost the same, isn't it? It really is. Very similar question. What is the slope of the curve at x equal to 2? Why is this one calculus? It's actually a curve. This one's a parabola, and in particular, it's simply not a line. Anything that I gave you here that's not a line would make it not precalc. Okay? So the first thing to answer is why, which one is this? And it's calculus. And the reason really is because it's not a line. And if it's not a line, you don't have a way to actually calculate the actual slope because it's not a line. So, what are we going to do? Well, we're going to use a numerical technique, and I chose this on purpose because I don't know that you've always seen this coming into this class. In fact, even if you've had calculus, you may not have seen this approach, and it's a really cool approach. Who does have a calculator with them today, a TI 83 or 84? Like, you're all grouped in the back. Oh my goodness. All right, raise your hands really high. How many do I have? 1, 2, 3, 4, 5. Did you say you had one, Frankie, with you? Okay, so 6. I have 7. Okay, so I'd like for you to kind of, would you who are in the back who have calculators move around for me? Would you guys stand up and go sit with somebody who doesn't? Okay, I've got one over here. How about the 3 of you guys? This one? Okay, you're going to have to get close enough to see each other stuff, okay? Take that. I need somebody to come over here with these 2 fellas. Can somebody do that for me? Okay, everybody's got to be able to see a calculator so you can see the keystrokes. Okay, is everyone close to a calculator and you can see one? Are we good? Can you come? Are you good? You can see from where you are. Okay, cool. All right, so I'm going to switch back and forth a little bit if I can get the document camera to cooperate. Sometimes I do and sometimes I don't. So that you can see the keystrokes on my calculator as well. There's a couple of things that you're going to need to do for me that you may or may not. This calculator that I gave you guys will already be set up this way. But if you've brought yours with you today, yours may not be set up this way. So give me a sec. Turn on this and see if it'll work. Nope, it's not going to. Okay, I'll walk around, it's okay. Okay, the first thing I'd like for you to do is I'd like for you to go into the table set feature. So the way that you do that is you hit the second button on the far left and the window button. Second window. So you should have a screen that says table setup. Does everybody see that on the calculator near you? Yeah? Okay, it'll be in a different place, and I don't know how to find it, so you might have to do some playing around with it to figure it out, but you'll be able to use it. You'll just have to do some legwork to figure it out. Okay, is everybody who has one of these say table set? All right, what you really need is you need the one that says independent to say ask. We're going to use this feature multiple times throughout the semester. It's the most helpful thing in the world. What it allows you to do is it allows you to choose inputs instead of the calculator choosing whatever random inputs were last used. Okay? Okay, so exit out of that screen. Once that's done, it should say ask on the first line, and it should say auto on the dependent line. Okay. I'm going to write one more thing on here. That was unfortunate. Okay. So we want to choose, or we want to find a slope at the x value of 2, correct? And I drew pictures on a previous slide where I let my points get really close together, didn't I? And I said if I could take points that get closer and closer together, I would get really close to the slope that I was really looking for. Does that make sense? So here's what we're going to do. You can fill this in on the table on your sheet. We're going to choose x values that are really close to 2. Okay, we're going to use the value 2 as well, but we're going to choose another value that's really close to 2. So one side of this table is going to be values that are a little bit bigger than 2. 2.1. And then I'm going to choose 2.01. Again, it's a little bigger than 2, but it's closer than the one before. And then I'm going to choose 2.001. It's really close to 2, right? Yeah. Okay, leave the column that says f of x and that says slope, leave those blank for the moment. And go to the other half of the table. I want to do the same thing, but from the other side of 2. So I'm going to choose like 1.9. That's really close to 2, but it's smaller than 2. And then maybe I choose 1.99. Again, smaller than 2, but it's getting closer than I was before. What do you think the last one's going to be? Yeah, 3 nines, 1.999. Is everybody good so far? Okay, we mentioned before that slope is y2 minus y1 over x2 minus x1, right? We did. One of these x and y pairs is going to be whatever happens when x is actually at 2. So we need to calculate that. So here's what you can do. Go ahead and grab your calculator. It's your first taste at doing this. If there's anything in the y equals screen, clear it out. But just click on y equals, clear out any equations that are there. Good. on your y equals screen, I want you to enter that equation. So 3x squared plus 2x minus 4. Everybody good with that so far? Know how to enter the equations. Okay, awesome. And then what we're going to do is we're going to actually input the value 2. Now, I am fully aware that you can plug the number 2 in and you can square and you can multiply by 3. I'm good with that. But if it's a square root, you might not be able to do it by hand, right? So I want to show you how to do it with your calculator because sometimes you can't calculate certain things by hand or maybe not very quickly. So if you hit table, so the way you hit tables, you hit the second button and graph. You should now have x, y1, and they probably have nothing in the columns. Does anybody have something in their x or y1 columns? Anybody else have anything in there? Okay, plug in the number 2. What'd you get? 12. It's 12. All right, so what we actually just found out is one of the xy pairs. So in this slope that I wrote down here at the bottom, what I have is and it doesn't matter where you put it at the first set or the second set, I'm going to put it as the second set. Your y value that you just found was 12. Your x value that you had entered originally was 2. Everybody good with that? Okay. Do you see 6 more x values on my screen and on your paper? You should. 2.1, 2.01, 2.001. And while you might have been perfectly fine if I told you plug in 2 and do it by hand, you might have looked at me and rolled your eyes if I said plug in 1.999 by hand, right? I mean, I would have if I were sitting in your shoes. But now you have the calculator that can do it for you. So in your calculator, put in 2.1, 2.01, 2.001, 1.9, 1.99, and 1.999. And once you have those, you can fill in your table. So for example, on my screen, on 2.1, I have 13.43. Do you guys have 13.43? Excellent. What did you get for 2.01? 12.14. How about 2.001? Does it look like that? It's okay? I mean, we would expect that the number would get closer to 12, right? Because the x value is getting closer to 2. So it makes sense that the y value is getting closer to 12. Like, that seems quite reasonable. Let's do the same thing with the 1.9s now. What do you get for 1.9? 10.63. How about 1.99? And 1.999? Again, are the numbers getting closer to 12? They are. So our expectation is met that the numbers are getting closer to 12. But you now have 6 more XY pairs. And you can use each of those pairs one at a time to calculate a slope. So I'll write the first one down. The first one, so I'll call it M1, would be to take the first y value, which was 13.43, and 2.1 in the denominator. And I can use those to calculate a slope. So if you want to go back into your regular screen on your calculator, you can do that. Make sure you put the numerator in parentheses. So you have 13.43 minus 12, close parentheses, divided by 2.1 minus 2. Okay, so there needs to be parentheses around these when you enter them into the calculator. Some of your calculators may already put them automatically in a fraction bar, in which case you don't need parentheses. That's a newer text type in the TI-84, some of the TI-84s. What did you get for a slope on that? What did the calculation end up giving you? 14.3. Good. That's what mine said too. Now you're going to do the same thing again for the second one, M2. So the value at the end doesn't change. It's still 12 and 2, but the value at the beginning does change. So this one's now 12.14 minus 12 on top, and I have 2.01 minus 2 on bottom. What'd you get? $14. And the reason it's exactly 14 is because the reality was that when we wrote down 12.14, we rounded. You didn't realize you were rounding, but you were. Your calculator only shows so many decimal places within that table, and if you go back to that table and like actually put the cursor on there, you'll see that there were more decimal places. Don't worry too much about it, but if they're using certain numbers of decimal places in like WebAssign and they want you to use 4 decimals, you're going to have to be a little bit more careful about that. Let's do the last calculation just so that we have it done as well. M3, which would be 12.014 minus 12 over 2.001 minus 2. Does it also give you 14? Yeah. Yes, ma'am.
Do you know if the web assignment truncates or rounds, and what do you do in your classroom?
It will tell you to round to a certain number of decimals, and that's what you'd want to do too. So you'll have to follow the instructions however they're stated. So if it says round to 4 decimals, that's what you'll do too. Yeah, so you will round. Yep. All right, let's do the other half and then we'll be done for today, okay? We have 1.9 with 10.63, so that will be M4. So 10.63 minus 12 over 1.9 minus 2. What did we get? 13.7? Okay. Then we'll do 1186. So M5. 11.86 minus my 12 over 1.99 minus the 2. What did that one give you? Is it 14 even again? Yeah, because we've rounded a little bit earlier. I'm going to show you how to fix the rounding if this happens in your homework. All right, the last one we expect to give us also the same 14. So M6, which is 11.986 minus 12 over 1.999 minus 2. Somebody double check just for us. Did it also give 14? You did? Okay, good. Okay, so here's what you're doing with this information. All of this is just the show the work stuff. Okay, that's all I've done. I haven't actually answered the question. What we're doing is we're looking as we go down this table, what slope value are we approaching? Now on ours, it looks a little funny because they actually both end up at 14 exactly. They aren't always going to end up at 14 exactly, right? They might get really close, but between the two lists, they should both approach the same list. And so our slope that we're getting close to is a 14. And that would actually be the answer to our question. So if you take a look real quick with me, just hit back onto your table so I can show you what I meant by finding the actual value where it didn't truncate it instead. Arrow over to the Y1 column and just on any of the Y values underneath it. So the second one, the third one, the fourth one. Do you see how it shows more decimal places? Okay, so however many decimals the problem is asking you for, make sure and report back to them however many that is as well. Does that make sense? So for example, just somebody find out for me, what was the second number? It wasn't 12.14. What was it? Really? When you are on top of the number. 1403. So just for a minute, pause with me and see what would have happened over here when I calculated the 12.14 if I had used 12.1403. So go back to the regular screen and enter this one, 12.1403 minus 12. And then divided by the 2.01 minus 2. what actually happens. What did you get? 14.03. We didn't get exactly 14. I mean, like, it's close, right? But it isn't exact. It's really 14.03. So if we were being more accurate along the way, if the directions asked us for 4 decimal places or whatever, our values actually wouldn't have gotten to 14 or gotten to there quite as quickly. Does that make sense? Excellent. So before next time, what do you need to do? You need to do several things. Number 1, you need to go print out notes for 1.2 and on, and they're all inside of Canvas. You should be able to print them all off right now if you want to. Number 2, you need to get logged in and set up on WebAssign. I mean, like, that has to happen today, because if you've got a problem, we need to solve it immediately, because the WebAssign homework that's due now from 1.1 is due on Tuesday at 9:30 in the morning. Before you show up at class, it will shut you down at 9:30, and you won't be able to continue working, okay? So WebAssign, you got to get logged in there and make sure you're all set up and ready to go, and you need to make sure it's working and start working on that homework assignment. Success Center times, I don't know if they've started yet this week. Does anybody know? Think they have? Okay. If they haven't, I'm still available in my office considerably today and tomorrow. Lots of office hours on Tuesdays and Wednesdays. So come see me if you have questions, technology or otherwise, and we will take a look.